All right, everyone, welcome to Calculus 3. So I'm recording this. I know some of you have had me already, but I'm recording this. I'll record all the lectures, and then I'll put them on YouTube. So you can go back and watch them whenever you want to. And that's all linked on Canvas. Anybody not able to get into Canvas yet? I accidentally forgot to publish the class until this morning. So it's there now. If you have any trouble getting into it, let me know. Eric, how's it going, man? Doing good? Doing better? All right, good. Oh, I forgot how to spell my name. All right, so my name, Robert D. Giovanni, and I'm gonna go ahead and open up Canvas so we can take a look at the syllabus. We're not going to go through the syllabus. Okay, I'm not going to waste that time. While I'm opening it up, please take one of the. I think I've made enough for you to take two. Everyone takes two of these. And then we'll start, after I go through Canvas, we'll have our first quiz over power series. I'm kidding. I'm kidding. Unless you want to do some power series. No? Okay. Sound good? Come on. Can you hit VGA on that thing? Or if it's ready VGA, switch it to HDMI and then go back to VGA. There we go, thanks. We're already wasting time. Okay, there it is. How about let's try and kill the one of those lights. Let's just see. Nope, not that one. Nope. Yeah, that's a little better. All right, so I already told you my name. I love this quote. They actually have that on a wall at the place where my daughter does gymnastics. I really just like this quote. Okay? There's a difference, I think, between doing math problems and saying, I finally got it right, and then getting to that point where you're confident enough where you feel like you're just not going to get it wrong. So there's a big difference. Let's bring up the syllabus. Here's the link, like I said, to the videos. They will appear here as the class goes on. You just click there, it'll take you to YouTube. Now, I've also worked out all the homework problems that you're going to be assigned out of the book. I've already worked them out on video, so they're all there for you. There's class files here. I have notes. If you go into the class files, I have notes for all the chapters we're going to cover, chapter 10, 11, 12, and 13. The complete notes are in there. This is just chapter 10. These are the notes, so you can print these out if you want. It's a lot. Okay. If not, you want to just keep it and look at it electronically, that's fine. You can use a laptop or something like that if you want to just follow along in the notes. The only thing is, if you're going to be doing that, just make sure that is what you're doing. All right, and I'll get to that as we get to some of the policies in class. There's also a lot of other stuff in class files. I think it might be worth looking at, except I can't see it because we're in VGA mode here. Let me see. That might be a little better. Okay, well, there's a bunch of stuff here. Hey, I thought we were all going to do, hey. All right, so the schedule's here. 3D graph paper, that's what I handed out to you just now. Formulas, all right? So these formulas are the formulas that you're allowed to use on your midterm and your final. But I'm going to tell you right now that, those formulas are probably going to become more extensive, especially Chapter 13. There are a lot of formulas in Chapter 13. And so normally on the final, I allow you to have like several pages worth of formulas. So we'll just get to that when we get there. Also, these notes that I use, they're here in PDF format, which means you can print them out. But the notes I use in class are actually interactive notes that I made using Mathematica. And so if you want, you can download. Mathematica has a player. It's called their CDF player. And so you can download my lecture notes and you can actually do all the animations at home. Like you can spin things around three-dimensionally. There's where those files are located. And then where it says course lecture notes, that's the PDF version of that. Does that make sense? Kind of. As we go through it, I'll kind of explain it. You'll see what I mean by interactive notes. And then I have a bunch of old stuff here. I would not look at any of those and be like, oh, his test is going to look like this old test. It's not. It's just, I just put old stuff out there. All right, syllabus. Like I said, I'm not going to read through this whole thing, but I will point out some important information. I provide you my cell phone number. Okay, my cell phone number is here, 210-273-1098. And I encourage you to contact me anytime you'd like regarding this class. Just make sure that if you text me that you include your name so I know who you are and what class you're in, because I have 5 classes. And so if you just say, hey, what was the homework tonight, or something like that, I may not know what's going on, all right? That's a 24-hour math crisis hotline right there, okay? So if you're ever in trouble trying to do something, you're stuck, and you need my help, just call or text. You know, if it's 2 o'clock in the morning, I just won't answer, okay? So don't worry about bothering me. I say that because I have internet students, so I kind of have to offer that to them, so I may as well offer that to you, right? Trying to scroll down here. My office hours. So these are the days and times that I'll be in my office for you to come in and get help if you'd like. You can come in unannounced, just come walk in. Before Monday and Wednesday before this class, I'm getting there, hopefully. I'm usually going to be there around 9, but I'm going to say 9:15 to 10:45. And then directly after this class, because we go from 11 to 12:40, I'm just going to walk downstairs and I'm available from 12:45 to 2:30. And that's it for Monday, Wednesday. Tuesday, Thursday, I'm there 11 to 12:30. Fridays, I did not put anything here. You can make an appointment. If I'm going to be on campus, but they always pull us into like committee meetings and things like that. So just, you know, send an email. If I'm free, I'll set something up with you. All right. Questions so far? Materials, that's the book. All right. How many of you took Cal 2 here? Okay, if you took Cal 2 here, it's the same book. So there's no change. If you did not, and you have an old book from a different class, just come talk to me. I might have 1 or 2 of these laying around, and I'll trade you yours for the semester and then give you yours back. Yeah, that's the blue one there. So we will be working out of that one, chapters 10, 11, 12, and 13. I'll go through I won't go through the outcomes and stuff. I'll get down to your grade, because the grade is a little confusing. All right? This is not set in stone, all right? Because I'm going to kind of let you all decide how this goes. This is my plan right now. My plan is to give you take-home exams, which I call mini exams, and some quizzes in class. And that all those together will comprise 40% of your grade. Then you'll have a midterm and a final, which will be 30%. Now the reason I do this is because we don't really have time to do 3 or 4 in-class tests. It just eats up too much of our lecture time. So midterm final, we only lose 2 days as opposed to 3 or 4 if I give you more tests. But there's a little thing here. If the midterm and the final exam grades are above 50%, that means you have to get a 50 or higher on both the midterm and the final for this to be the grading scheme. If either your midterm or final are below a 50, then it's an automatic fail of the class. So that just means that you can't just count on all this take-home stuff and then just think, these two don't matter. Does that kind of make sense? And I only did that because I've had this happen. Okay, especially on the final. Students will do great on the take-home exams, they do good enough on the midterm, and then they come in, they say, well, I only need like a 40 on the final to pass the class. But the material at the end of the class is very important, so I want students to know that material. So you have to get a minimum of a 50 on that final exam in order to pass. Okay? It's just to keep us all like foot on the pedal the whole way through instead of easing up at the end. Yes?
Cumulative final?
The final will not be cumulative. Nope. The midterm will cover chapters 10 and 11, and the final will be 12 and 13. Yeah. All right, no one wants to bail out yet? This is a weird grading scheme. I actually had to talk to the chair to make sure it was okay if I do this. And all right. Course policies, attendance, you need to be here. I will be passing around a sign-in sheet. What to expect. It just says that I use technology to record classes and put on YouTube, just kind of gives you a heads up. But I do have a policy on both your usage of electronic devices and your behavior in this class. And these are pretty hardcore penalties. So if you've got your laptop, that's fine. I'm not going to be always going around. But if I walk around and one time I walk around and I see you doing something other than my lecture notes open, 10% off your next exam, which would be probably the midterm, right? Just boom, right off the bat, 10% off. And you're asked to leave and you're counted absent for the day. So in other words, don't have your phone out. Don't be updating your Instagram or I don't know what's cool now, Snapchatting. But check it out, I'm in Cal 3 class and showing people what you're doing. No one cares, all right? So from 11 to 12:40, let's just stick to Cal 3. And then behavior, this doesn't happen that often, but if you're being disruptive or if you're sleeping, it's the same sort of thing. I'd rather you just go in the hallway, take a nap on one of those benches, or just not come to class than to come in here and sleep, all right? Questions on that? Okay. Dishonesty, cheating, blah, blah, blah. If you get caught, not good, right? The rest of this has to do with, this is stuff I have to have in the syllabus. But I think it's worth talking about this SOBI thing. This whole thing is just talking about, if you see somebody who's, I don't know, just seems odd to you. I know maybe in Cal 3 we're all a little odd, but if you see something strange, you see something in someone's backpack that, looks suspicious or, we all know what's going on these days. You just have to be attentive to what's going on around you. So if you see someone acting weird or displaying some behavior that makes you concerned, don't just be quiet about it, talk to somebody about it. And then that leads me to, we have to always have a plan if something happens, active shooter, that type of thing. So it's kind of funny because I've been talking about active shooters for a long time, since I started teaching, which is a long time ago. And students used to laugh at me because I'd be like, if someone starts coming down the hallway and they're shooting up the building or whatever, where are we going to go? And 10 years ago, people were like, this guy's crazy, right? Now everyone's like, okay, yeah, what are we going to do, right? So what we will do is, well, not here, not this window. This one right here. Okay, so that goes, we're on the 3rd floor, but that goes down to an awning There's an awning right there that's probably about what would you say that is? 10, 12 feet? You'll survive that fall. And then you have another, huh? Oh, the window doesn't open, but we will open it, right? All right, so, right. So we have a plan, okay? That side of the room, y'all are going to barricade the door for us. And this side of the room, we're going to throw a table through the window and we'll be out of here. And when we have cleared, then that side of the room can come.
Well, you might need to charge it first because it's, what, thick plexiglass?
Oh, I don't know if that comes into play. Then, we'll see. What's?
CHL?
Yeah, most likely somebody in here is carrying a gun too. Well, I don't want to know who's carrying. I don't want to know who's carrying a gun. In fact, if you are a license holder, you should not be advertising the fact that you're carrying, because then you'll lose that right. So, yeah. Well, I mean, there's a lot of different things that can happen. All right, but I'm one of those people who's like, let's at least have some idea of a plan, right? Because we don't want to be curled up in the fetal position underneath our desk, right? That's sitting there waiting for something to happen and never know that that window was an exit, right?
That's when you want Nathan here.
That's right. Yeah, you're right. You're right about that. There's certain people you do want in the classroom in that scenario. Okay, that's it. The schedule's here, and I think that's about all I want to talk about in terms of the syllabus. I do have an assignment that's due. It's online. It's right here at the bottom, due on August 31st. And it's just a syllabus confirmation quiz. You just go click it, and then you just answer a quick question. I read the syllabus. I understand the requirements of the course. And if you don't understand the requirements of the course, don't do this, because then if something comes up later and you said yes, then I'm going to hold you to that. All right? If you don't understand something about the class, just talk to me. I'll clarify it for you, because, like I said, I'm not going to spend an hour going through all these details. This is Cal 3. We're going to get down to business. Any questions? Sure?
Will you be gentle on grading?
Well, everything that I grade is everything's free response. There's no multiple choice here. So I need to see your work. You know, I need to see that you're making logical steps. Neatness counts here. All right.
What I'm asking is if you're going to get partial credit.
You always get partial credit, yes. Because it's free response, I always grade upon what I'm seeing. And even if there's an algebraic mistake, if everything else kind of flows, then, you know. But on the take-home exams, that's a little different than an in-class exam. You know, when you have an in-class exam, a mistake happens, it happens. When it's take-home, you should have time to go back and go through it again, double-check your work. It should be neat. It shouldn't look like you threw it together an hour before class. Another question?
We're going to get that packet.
The what?
The no packet.
There's no extras on those? Oh, you have like a dozen of them here.
I need them all.
Did you get one? Yeah?
Yeah, yeah.
Okay. All right, so everyone? Okay. All right, well, yes?
For the mini exams, what 8 on the grading book, is that set in stone?
The mini exams, it's not set in stone as 8. I'm glad you asked that question. I'm not sure how many mini exams I'm going to give you.
You just have them there.
Yeah, they're there just as a place filler for the grades. And I believe that there are mini exams in here already that you can actually see that are my old mini exams. And I will be using problems from those. All right, so the mini exams, I'll explain briefly how they're designed. I basically am taking the ideas of each section and I'm just cranking them up. And so I'm giving you a problem that requires you to really understand the underlying material, as opposed to a problem out of the book where it's just going to be like, oh, do this, show me you can like compute this, very mechanical. The mini exams are much more challenging. So I don't really want to say how many we're going to have yet, because I might kind of ease up on them a little bit. It's just going to, a lot of it's going to depend on how this goes with you guys. Like, I need to see where y'all are. Okay. That's it. Cal 3. What do y'all, what is your, what have you heard about Cal 3? What's the word on the street about this class? It's what? Cal 2 in 3 dimensions, okay. Heard it's easier than Cal 2. I heard that also. Anything else?
Multivariable calculus.
Multivariable calculus. Okay, what does that mean? Multivariable calculus. More than one variable. What do you mean by that?
Rather than having an x, you have x, z, y.
I thought in Cal 1 and 2, when we worked with like graphs and stuff, we had things like f of x equals, I don't know, let's go with something very simple, x squared, right? This is a function of a single variable, right? There's one input variable, x, and then there's an output variable here. We have in the past called f of x y, right? It's like y is equal to f of x, and we can graph this parabola. You could say this is multivariable, I mean, because there's two variables, right? I mean, there's x and y that's more than one variable. The idea with multivariable calculus for us is more like this, though. Instead of having a single input, we want to be able to have more than one input. So imagine that I have a function that instead of taking in a single value of x, it takes in an x and possibly a y, 2 inputs, and spits out something else like a z. That's more than one variable going in. So that is where that terminology comes from.
Would you have like an x comma y?
Yeah, the notation,
In the function.
we're going to get this, but the notation for that would be this. Okay. All right, what else have you heard about Cal 3? I've heard multivariable, I've heard it's easier than Cal 2, I've heard it's everything we did in Cal 2, but in 3 dimensions, is that what you said? Yeah.
Vector calculus.
Vector calculus, okay. So there's vectors involved here. These are all legitimate answers. So here's the way I'm going to try and introduce this topic for you, or this Cal 3. All right, let's go with Cal 1. Okay, Cal 1, major ideas? Limits, starts with limit, right? Differentiation, right? Those are like the main things. So Cal 1, you have limits, differentiation, I'm just going to put diff, and geometrically, we had things like, here's a curve, tangent lines, right? Tangent lines, and then we can talk about concavity. We can talk about whether or not it's increasing, decreasing, right? Increasing, decreasing. Local max, local min, or global max, global min. All of those ideas, though, were tied into this right here, right? The derivative, differentiation. And then when we got into Cal 2, I know there's a lot more here, right? But when we get to Cal 2, major ideas here, integration, right? Antiderivatives. And they were like the techniques of integration. And what else is in there? Series, right? How many of you, because I know this here, sometimes this doesn't happen, how many of you got into Taylor and Maclaurin series here? Yes? Okay, that's a decent amount. Okay. All right, integration. We won't need series in this class. So if you didn't get to see series, then you'll survive. Integration. How about geometrically? What was like one of the main ideas with the integration, the antiderivative? Yeah, you would have a function, right? And we could define the area of the region under there, right? And of course, we got more involved than that. We looked at the area between two functions, and then we did some revolving around different axes, and great. But I mean, this is like one of the basic ideas. So let me give you like the basic idea in Cal 3, all right? And it's not the only one, but it's kind of a basic one. In Cal 3, what we do is instead of having a function that lives on a flat sheet of paper like this, we extend this idea out to 3-dimensional space. So imagine this little cloth here, sitting in space, is kind of like a blanket, right? We call this a sheet or a surface sitting in 3-dimensional space, right? So if I've got this surface sitting in 3-dimensional space, like this, does that kind of look like my sheet in 3-dimensional space? then I could pick some point on this sheet and I could ask a question similar to this. See, with this, if we pick a point, then the derivative gave us the slope of the tangent line, right? But if I'm on a surface, right, what's that? If I'm on a surface and I pick a point right here, okay, on this surface, then what, can you still talk about tangent line?
Yeah, it'll just go through the surface.
It would have to go through that point, right, just like over here? But, yeah, see, you see the problem? I think you see the problem. The problem is that, what direction do I point in? Because in every direction there might be a slightly different kind of pitch to the line. Do you agree with that? And because of that, we need vectors so that we can get direction. So we will be talking about finding the kind of direction and magnitude of this pitch of this little line, but on a surface instead of on a flat curve, all right? All right, so that's one thing. And then another thing we can do is imagine taking this and projecting its shadow straight down onto the ground. Okay, so its shadow's on the ground, so let me try and project that shadow down. The shadow's down here on the ground. That's its shadow, okay? There's the projection of it. Kind of see it?
Is that shadow flat or is it
It's flat. This is flat on the ground, but it's got some curvy parts to it because this edge is curvy too. You kind of see this? All right, what do you think the analogy to this would be now with that idea? What's the volume of the solid that I just created? So if you project that shadow straight down and you fill in this void between the two, what's the volume of that? Got it?
What does the volume mean?
Well, yes, then now, remember how here area was area, but then you could say, like in physics, that you could determine like the work done if you had like force and, you know, depending on what the context of these variables were, this could have different meanings, right? Same thing with this. This can have different meanings. And then we get into vector fields, chapter 13, vector fields, and we start dealing with like these ideas of things like flux. This is like a physics term. You're trying to figure out like how much stuff is going through a surface at a certain point in time. Anyway, that's general. This is a very, very general introduction. The main thing is that we're going to go to three-dimensional space, all right? But it's not just Cal 2 in three-dimensional space, it's actually Cal 1 also in three-dimensional space. Okay, so where are we going to start? Chapter 10, right? And what's the title of chapter 10? I'm going to bring up my notes here. I realize you don't have the notes that I have to follow along with, but yeah. Is that the title of it? Okay. Go to the beginning here. 10.1, first section, is called the 3D coordinate system. All right, so I'm going to write something on the board here, and I'd like for you to kind of mess with it just to get you thinking again. This is not supposed to be like a trick problem or anything, okay? Let's see. Okay, I would like for you to find the solution to this. Solve for x. Then graph x. Graph the solution. Okay. Okay, well, I want you to draw the graph of that solution on your own piece of paper. And then we're going to go around, we're going to see what people have. Can everyone see the board okay? Is it too dark in here? You all right? As far as your comfort in terms of how you're seated, feel free to move desks around however you want. Okay, everybody have something? All right. So do we all agree with the solution being x is 2? All right, x is 2. And then I said graph the solution. So what do we have?
Straight line.
Straight line. So what do you want me to draw?
A vertical line.
A vertical line. So you want me to do like x and y axis like this?
Yeah.
And you want me to put at 2, you want me to draw a vertical line? Like this? Okay. Anybody have anything else? It's okay. I'm not going to tell you whether or not that's right or wrong yet.
You could graph 3x plus 4 and 2x plus 6 and find where they intersect at x equals.
I see what you're saying. Graph these as lines. Like treat this as a line and graph it. Treat this as a line and graph it. And they would intersect at x is 2. Okay? The solution, what I want is the solution. Give me a visual representation of the answer. One visual representation that's been given, okay, is this vertical line. I want to know if anyone else has a different solution.
Oh, well, you just put a dot at 2.
Okay?
Where y is 0.
Did you have something different?
The 3D plane, but at x2 the plane.
Okay, so let's do this. Let me go with yours first. You're saying I can do this, but just the dot at 2 instead. So let me do that. Let me do this. I'm going to draw it again, x-axis, but I'm not going to put the y-axis at all. I'm just going to put 2, and I'm going to put a dot here. Right? Okay. And then got another one, 3-dimensional, but we haven't talked about that yet, so let me hold off on that. Okay? Which one of these is right? They're both right, but this one could actually be wrong. And this one could also be wrong. So that's why I want this to be our first example. Because if somebody says to you x equals 2, and they ask you to graph this, all right? Then if you draw a number line and you say, you call all the values on this x, and you say, oh, the one that corresponds to 2 is that dot, that would be correct, is if you're living in one-dimensional space. If your universe is one-dimensional just meaning one measurement of length, that's it, then that would be correct. So this is correct in one-dimensional space. Right? This is correct. But if the universe that you live in is two-dimensional, then this is correct. So let me show you that one over there again. What if I drew this? X, Y, 1, 2, and I put a dot here like this. So my universe is two-dimensional, and I say that that's the answer. Is that right or wrong? This would be wrong because this is one answer, but it's not all of them. Okay, because in order to satisfy this equation, what you need is for x to be 2. And if I pick any point along this vertical line, x is 2, right? The y is different, but the y doesn't appear in the equation, so it's irrelevant to us. All right? So this is correct in two-dimensional space. Now I'm going to start writing my dimensional space differently. This is correct in R2. Okay, you don't need to box it, but I'm just pointing out. R2 means two-dimensional space. What would this be? What would one-dimensional space be? Just R. Okay, that's one-dimensional. You don't need to put the 1. And then that begs the question, well, what about in R3? What's three-dimensional space? So that's what we're going to start with, this section, 3D coordinate system. But I wanted you to just understand that if you have an equation and it has a solution, and you're asked to represent that solution in one-dimensional space, you may have one single unique answer, right? There's only one point that satisfies this equation in one-dimensional space. In two-dimensional space, there are actually infinitely many points that satisfy this equation. So now this matters to us. In Cal 3, what dimension you're living in matters. All right. All right, so that's kind of what I illustrate here in my notes. I have a mouse that I have, a wireless mouse, where I can just control all these notes, but I don't know where it is. I brought it with me, and it may have fallen out of my bag in my office, so let me just make sure it's not. It's not here. All right, so I've got to do this. All right, so if we have a point in R1 is obviously just something that lives on the number line. Points in R2, you have what are called ordered pairs, right? So we're very used to seeing notation like this. If you have a point, it's like the point 2, 3, right? This is an x value of 2, y value, x is 2, y is 3. That's R2. Now, these things become very important later, so that's why we have to make sure we understand it. If I write now x equals 2 like we had earlier, but we're in 2D, this is a vertical line, right? This is a vertical line. And what we say here in this case is that y is free. It's what we call a free variable, because the y doesn't matter, right? If x is 2, it does not matter what y is. We can pick any value of y, and we would satisfy the equation. Oops. There we go. All right, what if we do different equation and we do something like y is equal to -2? Then x is free, and this is a horizontal line, right? Horizontal line. This is horizontal line. This is a vertical line. Now, let's pay attention to something here. When we have a vertical line, right, would you agree with this statement? That a vertical line is parallel to the y-axis? Yeah. Yes? Okay. And horizontal lines are parallel to the x-axis, right? Okay. We're going to have something similar to that in a second. Okay, some other lines that we're familiar with. This is a very important line. Y equals x, right? That's your identity. Can anyone give me any property of the identity or where it came into play at any point in time? Anything that has to do with the identity that is kind of cool about it. Vertical line what?
A vertical line always forms the right triangle with the x-axis.
Okay. Yeah, but that could be with any line. What I'm saying is this specific one, y equals x. It's called the identity. It's very important to us.
It goes to the origin.
It's a perfect diagonal. Now this is not drawn to scale, so it doesn't look like it, but this is 45 degrees. The thing I'm thinking of has to do with inverses. Okay, so when you have a function that's invertible, which means it has an inverse, if you sketch both the function and its inverse on the same axes, they are reflections of each other over this identity. So if you kind of tilt your head and look, they would be mirror image. All right, this is just to remind you of some of the lines. I mean, y equals 3x, it's just a line. I only did those because I wanted to show the difference between a positive slope and a negative slope. Just make sure we understand. One goes up, the other one kind of pitches down. And that's it. All right, now we're ready to talk about three-dimensional space. All right, so when you're thinking about 2D, let's go back to 2D. In 2D, 2 dimensions, in R2, our natural setup is an x and y axes. And then we split this into 4 separate regions, and we called those the quadrants, right? Quad meaning 4. And where's the first quadrant? Top right. So this is quadrant 1, I'll say Q1. And then this is quadrant 2, quadrant 3. Why did we do it this way? This seems kind of ridiculous that we went counterclockwise starting with the top right. Why didn't we do like 1, 2, 3, 4?
Increase of angle.
Yeah, that's right. If you have an angle, right, we always orient the angle out the x-axis and call that angle 0. And if you start increasing your angle, you want to go naturally through the quadrants, right? You want to go through 1, then 2, then 3, then 4. You wouldn't want to go through 2, then the 1. You know, that would be weird. So that's why we do it that way. Make sense? Okay. So R2 consists of all ordered pairs where you have the form xy, right? All the different ordered pairs fill up this entire space. Now R3, we run into a problem. Why do we have a problem? We need another dimension, right? And I'm trying to draw this on a board. And this board is only 2-dimensional, so I have to figure out a way to draw it to make your eyeballs, both of them, see 3-dimensional space on a flat sheet of paper. So that's why I gave you the graph paper to help. The way I recommend you try and draw 3-dimensional space is you draw kind of like a squashed down X. Don't do this. Don't do that. Squash it down a little bit. Or if you'd like, stretch it out this way. And then draw a vertical line through. Now this point in the center we'll call the origin. And then we need to label our axes. And you have some options here. I did on that paper, I chose to put x is this axis, and I put a little plus here, meaning this is the positive direction of x. And then this axis right here, I chose to be the positive direction of y. And then up was the positive direction for z. Now I say you have some freedom. I don't mean complete freedom here. You have some freedom. Let me show you a different way you could have drawn this. You could do, I'll do that squash down x again. You could have done x positive here, y positive here, and z positive here.
So Z positive if X and Y were just like in 2 dimensions as we're used to see them, the positive Z axis will be towards you.
Yes, I'm gonna do that right now. I want to put these both up here first, and then I'm gonna go walk to the corner of the room to show you what I'm talking about. So imagine now, and this is not going to be on camera, but oh well. Our traditional XY is like this, right? And this was X positive and this was Y positive. Let's just look at this first quadrant right here. And I'm going to go stand in the corner of the room. This point right here, I'm going to go stand at it right here. It's going to be right here. Okay, I'm standing on that point. So I'm like this. Here's my head. My feet are on the ground. Okay, so my head, feet are on the ground. So positive X is that way, right? Positive Y is that way. And Z is coming straight up like this, right? Now I'm going to probably walk to this corner of the room several times throughout the semester. We all need to agree that this is going to be positive X, positive Y, positive Z, all right? Negative x takes me into the other room, right? Negative y, I go back that way. Negative z, I'm going to go down below this floor. Okay? So do you see that these two pictures are exactly the same thing? Except if you take this one and you just kind of imagine taking the z-axis and turning it like this, you get this one, don't you? It just rotates that around, pulls this thing around. So those are two ways you can draw it. There's more ways. Let me show you another way. A lot of times in physics they do this. From now on, when I write x, y, z, I mean the positive direction, okay? The difference between these is that this looks like the old xy plane, and then this little line coming out. It's still three-dimensional space. That looks kind of more like the corner of the room, doesn't it? Okay. Any questions?
Does z always have to be vertical? Because it kind of, I guess I feel more comfortable with y staying vertical, x being horizontal, and then z being in and out of the paper. Because that's more of having your paper kind of like this and z being like that. And
You can draw it different ways, but you have to follow what is in the notes here, which I'm about to put up. I'm going to put up after I say it, which is called the right-hand rule. Okay, we have a rule that your axes must follow. It's your right-hand rule. And this is just something that we all agreed upon. But let me try and lead to the right-hand rule by asking you to consider something. What if I change this right here? Let's leave this as z positive. Let's make this y positive, and let's make this x positive. And I'll get rid of this one. Are these two the same? Is it okay for me to use this versus this?
No. Z positive will be pointing down, right?
Well, in this case, but I'm saying it's this, though. I'm saying it's this. Is that okay? It's not. Why not?
According to the right-hand rule?
Yeah, but why does the right-hand rule tell you you have to do it that way?
If you do it like differently, every one of us will have a different answer, like for Z.
Okay, so there's something happening here where if we all just have this complete freedom to label our axes however we want, we will run into a problem where our answers won't match up. Now, let's take one step back. Let's go back to R2. Standard way of writing R2, x, y. Remember, those are positive, right? If I go over here and I try and be a rebel and be like, I don't like it that way, man. I'm going to do it a different way. So I decide I'm going to go like yx, and I'm like, yeah, okay. Is it okay, or does the universe fall apart, or is this okay?
Yeah, it's okay.
Does the y have to be where?
on the other side, like y positive on the left side is x.
That's what I'm asking you. Does it matter? I just told you a second ago that with three-dimensional space, it mattered, right? Because of this rule, and the answers won't match up. I haven't gotten into more detail on it. I will. But let's go back to R2. Does the way we label axes matter? Does it change the mathematics? Is it going to make us get wrong answers or incorrect answers, or our answers won't match each other's? It does not. Doesn't matter. And here's why. Because as long as you can turn, rotate, and do some sort of transformation and turn this picture into this picture, you're good. Okay, so let me see. How could I turn this into that?
You have to flip it and then turn it.
I'd have to flip it and turn it. So that might be hard for me to, for everyone to see. So let me try a different way. When I look at this, when my head's like this, what do I see? Y up, X to the right. Yes? Okay, I'm gonna go out of the room. Y'all come with me, right? We're gonna walk out the room. We're gonna go over to the other room. We're gonna come in that door and we're gonna look at the board from the other side and imagine it's transparent. Are you with me? Are you standing on the other side of the room with me? Okay, and we're gonna look at this picture. When we're looking at this picture, what do we see? X up, Y like this, right? Turn your head, and what do you see? What do you see this way? X, and what do you see that way? Y. Now, if you can flip it and rotate, but the idea is that if you can just take this picture and look at it from a different perspective and still get this picture, then it's okay. The problem is in 3 dimensions, you can't do that. You can't just come in from a different angle and see the same picture. These are called isomorphisms. When you can transform a space into another space without losing anything, it's called an isomorphism. In 3-dimensional space, there is no isomorphism if you get if you label the axes arbitrarily.
Labels have to be, or the axes have to be labeled properly so that no matter what perspective you're looking at in that 3-dimensional space, you still get the same.
That's right. Your perspective, anywhere you look at it from, it's going to be the same. Now, the right-hand rule is a rule that we all use, but it could have very well have been the left-hand rule. All right? It's just something we all have to agree upon. Just like order of operations, you learned order of operations, right? Parentheses, exponents, multiplication, division, all that stuff. That was an agreed upon way of doing things. It does not have to be that way. We could have agreed upon something else. So the right-hand rule says that when you are drawing 3-dimensional space, when you draw a 3-dimensional space, what has to happen is that you, using your right hand, assuming that you have a thumb, your thumb, if you point your thumb in the positive z direction, then your fingers must curl from the positive x to the positive y. So right hand z-axis positive. Now when I curl my fingers, I should be going from positive x to positive y. So let me go stand over here in this corner. If my thumb is pointed positive z, that's that way, right? This way. And then look, my fingers are pointing down the x-axis, positive x. When I curl them, they're going to curl towards positive y, right? Now, if I try and do this differently, this is what I was trying earlier. Oops. I tried to say, can I draw it like this, right? So point your finger in the z direction, positive z, curl your fingers. If I curl my fingers, where am I going to go from? Positive y to positive x. That's not the right-hand rule. In fact, the only way to get my fingers to curl from positive y to positive, or positive x to positive y here is to flip my hand over, and that means I'd have to have my positive z be down there and not up there. So that would work. All right? How many of you have seen the right-hand rule? Yes? Okay. I can tell. I remember a class I took in undergraduate, an undergraduate math class that I took called Non-Euclidean Geometry. And we were having to do some things where we were, I don't even remember. But I went up and was talking to the professor because I was having trouble with this problem. And I was like, yeah, you know, I'm using the right-hand rule and all this stuff. And she looked at me, she was like, that's your left hand. I was like, oh, shit. Because I'm left-handed. So I was using, and I messed it up. Oh, well. So if you're left-handed, it's the right-hand rule because there's more right-handers out there, I guess. Now let's go back and talk about this 3-dimensional space. And I'm just going to stay here to do this, see how this works out. Yeah. There it is. Okay. I know this is kind of a little slow today, but that's just the way it is, all right? All right, so here's 3-dimensional space. I'm trying to pop it out of there. Let me try and rotate it around so you can see. There we go. There's our positive x, positive y, positive z. All right. We need to talk about what points are in here. So let's take a point. Let's try and plot the point let's go 2, 3, 1. Okay? So on your graph paper, I want you to try and do this. I want you to plot 2, 3, 1. So I'm going to try and do it up here like this. And you see on your graph paper that has those lighter lines? The way you do this is you walk out, try and draw these lighter lines. It's really kind of a mess, isn't it? So when you're trying to plot the point 2, 3, 1, that means you're going to go out the x-axis 2 units, right? So that means starting at the origin, the x-axis positive is this way. I'm going to walk out 1 unit, 2 units, right? So I'm right here now. Then I'm going to walk out 3 units on the y direction, right? So that means running parallel to the y-axis, I'm going to walk out 1, 2, 3 units. So now I'm here. And then where? Up 1 unit. So how far is 1 unit? You can't, it's kind of hard to see it, right? But you just have to go up 1 and put a dot. Okay. I want you to do another point. I want you to do 2, 0, 0. Got it? So that just means come out the x-axis right there, and then don't go anywhere, right? So we got this point right here. All right, let's draw, how about 0, 2, 2. Does everyone kind of understand what you're doing? You know how you're moving around on there? Okay. 0, 2, 2. So don't move on the x-axis. 2 units this way on the y-axis. And then up 2 units. About 2, whatever that is.
So with a properly drawn graph, we're going to sometimes run into points where
They're on top of each other. Yeah, absolutely. The question is, if you draw a graph, even if you draw it properly, you may have 2 points that look like they're in the same place. And let me try and explain why that would be. Let's say that, let's say that you're an observer, and let me see. So here's like a little box sitting in 3-dimensional space, right? So from where you're sitting, if I turn this properly, you would not be able to distinguish this front point from a point in the back, right? Because from your perspective, they would overlap each other. And because of that, we're limited, right? I mean, look, we're trying to draw 3-dimensional space on 2-dimensional space. It turns out that it's mathematically impossible to do it. Like, you cannot mathematically put 3-dimensional space onto 2. It doesn't work, all right? So like, have you ever seen a map of the world? Right? It's impossible to put that map of the world onto a flat sheet of paper. So when you look at a map, this is just random useless information, but when you look at a map, which you never do anymore, right? But if you were to open up a map and you look at it, you know how there's a little legend that shows how many miles, right? There's 2 types of maps. There's a map where the distances are correct. So if you look at this map of, this is the United States, please don't be jealous of my abilities. But if you break out a map and it has city here, and you measure that distance, there's a little legend that tells you that distance, right? One type of map would be correct in terms of if you measure between 2 cities, it will give you the correct distance. What it will not give you, what you sacrifice for that, is if there's another city, that distance will also be correct, but what won't be correct is the angle between the cities. Okay? The angle would be off. Then there are other maps where the angles are correct, but the distances are incorrect. So if the shipping, like back in the day when the ships, right, going along the sea, which map do you think they wanted? The one with the correct angles, because then they could point and go, right? They did not want a map that gave you correct